in this movie, in this lecture, whatever, I want to kind of quickly go over constitutional isomers in a more practical way, especially considering it just bothered me that I botched the molecular formula. Anyway, let's actually do an exercise here where we take a molecule like heptane and we say, draw all constitutional isomers of heptane. Draw all constitutional isomers of heptane. That's a somewhat fair question. It gets to be fairly unwieldy the bigger the chain gets, and it gets to be really boring. So it's kind of limited to like pentane, hexane, and heptane, if I'm completely honest, as fair game. So what we want to do is try to catch all of the constitutional isomers of heptane. So first thing I always like to do is draw my straight chain molecule. And this is where we have an extended chain out to 7. Okay, and that's the only structure we can draw with a 7 as our longest chain. We could then go on to 6. So we're at 6 carbons, and what I'm going to do is stick my one missing carbon onto, instead of C7 at the end of the chain, I'm going to stick it at C6. So it's as if I pulled this carbon atom and moved it into this position on my ring. As opposed to being connected to C6, it's connected to C5. And what I do is I just do that as much as possible. For pentane, I could only do that once, but for heptane, as things get more complicated, I can continue to do that and do that and do that. So I've got it at 4 now. I'm again at 6. So 1, 2, 3, 4. And then I could go into here. Now what I want to do is stop after a few of these. You generally can't do this more than a couple of times before you start including duplicate structures. So if you look, I wrote, I hit C4 if I'm counting from left to right, but if I'm counting from right to left, then this is C4 again. So this structure is actually a duplicate of this structure. So I need to cross that out. That one will not be included. So we've written 2 structures where the longest chain was 6, and we're going to decrease it down to 5. Okay, so we have a longest chain of 5, and now we can add 2 of these groups. So instead of, so you can, there's a few ways you could do this. I'm going to attach our 2 missing carbon atoms now to C4. What happens if we add them to C5? Well, if you do that, you get the same structure as what is up here. So that won't work. So they're at C4, and now they're at C3, and if I move them to C2, I get the exact same thing as C4. Alternatively, instead of having the 2 single chain carbons sticking together, they could be separated from one another. So let's say we put one here, and we could put one there. And then if we put one there again, we could put it here. I believe anything else that I do at this stage would be a duplicate, although you should prove that to yourself. So now I've hit all of the possibilities with 5 carbons. Now what about 4 carbons? Okay, so 4 carbons, it gets tricky. Now we're missing 1, 2, 3. Now let's check. This one indeed looks new. So I took the 3 missing carbons off of my longest chain of 4 and stacked 2 at C3 and then 1 at C2. If I stack 2 at C2 and 1 at C3, actually those 2 structures are the same. They've just flipped horizontally in space. I know this is hard to see. The saving grace of all of this is I can't ask you anything harder than heptane, really. And you could check the discussion problem sets. There's practice of the fair game before it just gets too unwieldy on the high end and too boring on the low end. Okay, now similarly, you might say, well, what if I put them all on the same carbon atom? That is to say, if I've got a 4-carbon chain, I stick them all on the same carbon atom, 1, 2, 3, ack. Hopefully your alarm's going off. At this position, we broke the octet rule. That is to say, we only want 4 bonds to carbon. Any more than that, we'd have 10 electrons, and we can't fit that in the second shell around our atom. Okay, so I believe, and somebody may correct me, and I'm excited to hear that, I believe I've hit all of the constitutional isomers of heptane. So it's kind of going through this analysis of slowly making the chain shorter. If I go down to 3, I'm going to get to a ton of duplicates, because as you get to, and we can just go through one of these, if I get to 3, I need to somehow pack this with 4 carbons. I can only put 2 in the center, and then I'm left with 2 more at the ends, maybe? Oh, look, that's the same as this molecule up here. All right, that's not going to work. If I put 1 out here at the end, oh, that's the same as this molecule up here. You can't make the chain really too short. I still haven't figured out a systematic way of doing this other than just kind of practicing it and thinking through it. But anyway, we can get to a systematic approach to determining whether 2 molecules are the same or not, and that's through nomenclature, which I teased about in the last lecture and we'll actually get to in the next one. So the next one, next lecture will be on nomenclature. It's going to feel kind of, hopefully it feels systematic, but it's going to feel like something we're just memorizing. We're not really learning chemistry. And I can't disagree with you too much there, but it is very useful, especially when we're trying to determine if 2 molecules are the same or not.